Okay, welcome everybody. So we are very happy to have Onkar Parrikar, who needs no introduction. He's known to all of you, and he's going to tell us about islands with gravitating paths and the ER equal to EPR. So as usual, please unmute yourself and ask questions. And so Onkar, please.
Yeah, thank you, Ananda, and thank you everybody for inviting me to talk to you all about this paper, which came out on the archive a couple of months back. As Ananda said, please feel free to interrupt and ask questions and yeah, make comments and so on. So this work is based on this paper, as I said, with Louise Anderson and Ronak Soni, who are also here at Stanford. Um, so the brief outline for the talk is going to be as follows. We'll start with an introduction, then we'll review some previous work which is relevant for the purposes of this talk. Then we'll come to the main topic of discussing islands with gravitating paths and the connection with the ER equals EPR paradigm. Finally, we'll briefly mention some other models of similar physics involving gravitating paths, and then I'll conclude and discuss some open questions. Okay, so let's start. So as you all know, in some recent developments, for example, in these papers, a lot of progress was made on the information paradox, especially in the context of holographic systems in asymptotically ADS spacetimes coupled to external paths. And so just sort of to take a step back, recall that in Hawking's original calculation, the state of the radiation from the black hole appears thermal to an asymptotic observer. And so if one computes, say, the entanglement entropy or the entropy of the radiation emitted from the black hole, then as a function of time, it just keeps growing linearly because the radiation appears thermal for all times. And so as a function of time, you collect more and more radiation. And so the entropy keeps growing with time as a more or less linearly. Okay. And so this is sort of a prediction that one obtains, the red line here, a prediction that one obtains from Hawking's calculation for the entropy of the radiation. And at a time which is called the page time, we run into a contradiction because after the page time is defined basically as the time at which this entropy of the radiation is equal to the black hole entropy. And so at this point, you run into a contradiction because now the entropy of the radiation, or the answer from Hawking's calculation, is greater than the entropy of the black hole itself. And so this cannot be if what we are computing is a von Neumann entropy. Okay, so in fact, the prediction from quantum mechanics suggests that at that time there is some sort of a turnover, and the entropy starts decreasing with time, or it stabilizes or saturates after that point if the physics is that of equilibration. So, in these recent papers, there was some progress in understanding how this sort of a turnover or this so-called page curve is obtained from a semi-classical gravitational calculation. In particular, in this paper by Almeri, Mahajan, Maldacena, and Zhao, it was argued that if one is interested in computing the entropy of some bath system or some, so the bath here is we are imagining some sort of environment which the black hole is coupled to and at asymptotic infinity and is absorbing all of the radiation that is emitted from the black hole. So the insight in this paper was that if one is computing the von Neumann entropy of such a non-gravitational bath, nevertheless coupled to a gravitational system, then what one must do is one must include or one must slightly modify one's formula for calculating this one-dimensional entropy by including what they call islands. And I'm sure you all are familiar with this formula by now. The point was to include sort of disconnected regions of the gravitational space-time inside the semi-classical subsystem, so to say, and to sort of extremize this generalized entropy of a surface like this somewhere, say, in the bulk of the gravitational space-time, and then compute all such extrema and find the minimum of them. Okay, so here, for example, is a cartoon of what happens at page time in an evaporating black hole setup. What one finds if one uses this particular formula for the one-Neumann entropy of the radiation, one finds that at page time, there is a new, sorry, I should say before page time, the quantum extremal surface corresponding to this formula is the empty surface. And so one is just computing the entropy of the sort of semi-classical degrees of freedom in the radiation or in the path. But after page time, one must include a sort of island region. A new quantum extremal surface forms in the space-time, and one must include an island region from the space-time within the entanglement wedge of the radiation. And if one computes the entropy using this formula, then at page time, as I said, there's a phase transition to a new quantum extremal surface, and the entropy growth saturates. Okay, so the Hawking paradox is averted. Now, subsequently, so this formula was of course stated in this paper, but then subsequently it was a derivation of this island rule, if you like, was given using what are called replica wormholes. So we'll discuss these replica wormholes in some detail later, so I won't try and explain them right now. One point I should emphasize is that most of these works considered baths or environments which were themselves taken to be non-gravitating systems. So our main motivation in this paper was to ask what happens if we consider instead a gravitating bath. So not only is the asymptotically ADS space-time here, the black hole space-time gravitating, but imagine that also in the bath region, we have dynamical gravity, and then what's the physics of that setup? And I suppose I should, as an advertisement for the rest of the talk, I should mention that this is not just sort of a minor, it may seem like a minor modification, but in some models, or at least in one model that I'll talk about, it has a pretty dramatic effect on the physics. And what one finds is that instead of finding an island like so, what happens is that one finds a Hawking page transition in the geometry, in the gravitational saddle point, and instead we get an ER equals EPR type bridge connecting the bath region, if you like, with the black hole spacetime. Okay, so that is going to be one of our main results that I want to get to slowly. And the point being that this sort of setup is a concrete realization, if you like, of the ER equals EPR paradigm, where entanglement leads to a connected geometry in the context of these toy models. So we'll get to this slowly, one step at a time.
Onkar, in this picture that you're talking about, is there a black hole in the bath or no?
Yes. So the thing I'm going to consider here is in the toy model, as I said, the bath is gravitational. So the simplest toy model we'll consider is where we have two black holes, and they're entangled with each other. Okay, and that's the situation where we'll find a bridge forming between the two black holes. Any
So
other
I have a question. So is this a bridge formed after the page time?
Yes, it is.
Okay.
Exactly.
So,
So
before the page time,
indeed
there is
after that's
no.
correct. That's correct. That's correct. So before page time, the gravitational saddle that dominates is two disconnected black holes, and after page time, the connected saddle dominates. So yeah. So I'll explain those details shortly. But
so in a sense, it is kind of like you have a single giant two sides after page time. That's what sort of is that a reasonable way to think about it?
Could you repeat your question?
I was asking that it is a bit like after the page time, you have a single giant wormhole connecting the two.
That's
correct.
That's correct. That's correct. Okay. Yes. Okay, yes. That's it.
So
that's what this cartoon was meant to depict, but I'm afraid it's not very good. Okay. Any other questions? Okay, great. So then in that case, let me begin with first a brief review of a model that was introduced in this paper by Pennington, Schenker, Stanford, and Yang, also sometimes called the West Coast paper. And so as I said before, this model will not have any gravitating baths. The bath
Sorry, can anybody hear me?
Is there a question?
No, I think you got disconnected for a couple of seconds.
Yeah, I did. Yeah. Oh, sorry. Can you hear me now?
No, I think he was fine. I think maybe the problem was on your end, Anindo.
Okay. Yeah, sorry. Okay, carry on.
Okay, sure. Sounds good. So the model that we want to consider is sort of a black hole geometry in JT gravity with an end of the world brane behind the horizon. So here is the Euclidean picture, and here is the Lorentzian picture. So I'll explain these pictures a little bit more below, but just wanted to sketch a cartoon here. So of course, the action for JT gravity is written as follows. There is the dilaton, which enforces the R equals -2 condition. So the geometry is ADS. There is this extremal entropy term where chi is the Euler characteristic of the geometry that one is considering. And there's a boundary term at asymptotic, the usual boundary term at asymptotic infinity. And finally, this is the term which enforces it's like sort of a term on the world volume of the end of the world brane, which enforces the tension. This parameter mu is the tension of this end of the world brane. Okay. The asymptotic boundary conditions are completely standard, so I won't repeat them again. I suppose I should remind you that the boundary condition one enforces on the brane or on these end of the world branes, which are drawn here in red, are as follows. So one has k equals 0, the extrinsic curvature of the brane equals 0, which essentially says that this brane follows a geodesic in ADS2. And in addition, one also finds a condition on the dilaton. So the normal derivative of the dilaton has to be equal to mu. And that, if you work it through a little bit, in terms of ADS Schwarzschild coordinates, it turns out that that condition enforces that the turning radius, or the minimum radius, here, for example, the minimum radius that this brane gets to in the bulk is equal to mu, this tension parameter. Okay, so that's just some basic geometry. Now, the interesting thing about this model is that what one imagines is that on this end of the world brane, there is some internal degree of freedom, and we will just label these internal degrees of freedom by some index I, and this I will run from 1, 2, and so on through all the way through k. K is some integer. Okay, so k is just the number of degrees, the number of internal degrees of freedom, which we will label by I on, and these are sort of the internal degrees of freedom of the end of the world brane. Okay, so one way to think about
Is there any
yes.
Is there any constraint on the tension of the brane, whether it's positive or negative, or does it matter?
So it's positive. So we are going to take it to be positive. I don't think it matters so much, but for our purposes, we'll take it to be positive, so that these so that we the brane curves inwards, and we can consider like black hole solutions where the brane is behind the horizon and so on. So okay. Yeah, that's all.
Thanks.
Yeah. Any other questions? Okay. Good. So so one way, so I was saying that this brane has some internal degrees of freedom, which we will label by I. And one way to think about these internal degrees of freedom is as follows. So just from the boundary quantum mechanics point of view, if you look at this picture again, forget the brane for a second, but just if you look at the asymptotic boundary, what is happening is that you have, in this Euclidean picture, you have sort of you have these two endpoints, and you have a Euclidean time segment that runs between these two endpoints. So the way to think about that is in terms of an overlap. So you imagine cutting that circle, this circle which runs between these two endpoints, into two pieces at say tau equals 0. So let's imagine that you cut it at a midway at the midway point on this segment, call that tau equals 0 or t equals 0. And so the lower half portion of that Euclidean segment runs from this endpoint I to tau equals 0. We can interpret this as e to the minus beta over 2 times the Hamiltonian, acting on some initial boundary state, which we can label with I. Okay, so think of this boundary state as being the boundary condition specified at this endpoint, and then you time evolve in Euclidean time with for a Euclidean time of beta over 2, and that generates this lower half segment. And similarly, the upper half of this Euclidean segment can be thought of as some boundary state J at this endpoint, which now specifies the bra. And again, Euclidean time evolved for beta over 2. And then finally, the full thing can be interpreted as the overlap between these two states. Okay, so it's just the overlap between psi I and psi j, and that generates this full Euclidean time evolution from the boundary state I to the boundary state j. Okay, so these I and j, these boundary states, are sort of the things which are that's where the data is for deciding what the internal state of the degrees of freedom on the end of the world brane is. Okay, so you could think of these I's and J's, the labels for the internal degrees of freedom on the brane, as being specified by these boundary states. So for example, this overlap in the boundary quantum mechanics will now be computed on the gravity side by just finding a gravitational solution to JT gravity with this asymptotic boundary condition and an end of the world brane connecting these two endpoints. So the picture looks like this. Okay, you have this asymptotic boundary segment that's being filled in here by ADS2, and then these two endpoints are then connected with an end of the world brane, which satisfies the end of the world brane equations of motion. Okay, one last thing I have to tell you is that in the bulk, you can only have an end of the world brane if the two labels I and J are equal to each other. So in other words, there is a propagator for these internal degrees of freedom on the end of the world brane, which is this delta ij. Okay, that will be our prescription for the propagator on the end of the world brane. Okay, so those are going to be the rules for how to compute overlaps like this in quantum mechanics from a gravity from JT gravity. Now, in case you're wondering where these rules come from, then sort of as a minor comment, I should say that you could think of these states I, these boundary states I, as some linear superpositions of energy eigenstates in the boundary quantum mechanics. And you're probably familiar with the fact that JT gravity is dual to a matrix model. So a model where you average over the Hamiltonian. So the Hamiltonian is not fixed, but you have an ensemble of Hamiltonians. So what these boundary states correspond to is essentially, in a similar spirit, they correspond to random superpositions of energy eigenstates. Okay, so in other words, if you consider random superpositions of energy eigenstates, so these C's, these coefficients C's are Gaussian random variables, and these F's are some fixed functions of the energies. Okay, and the information about the tension goes inside this function F. So if you consider random superpositions of energy eigenstates like this, and you compute this overlap in quantum mechanics using the ensemble average prescription of Saad, Schenker, and Stanford, then one finds that the gravity dual of that calculation is precisely given by these rules, where you find a dual ADS2 geometry and cut it off with an end of the world brane going between the two endpoints, with the propagator being delta ij. Okay, so if you want more details on that, you can find that in an appendix of the West Coast model paper, the Pennington, Schenker, Stanford, Yang paper. So I won't go into any more detail about that, but my main message here is that these are going to be the set of rules that we will use to compute overlaps like this from a gravitational point of view. Are there any questions about that? Okay, so if not, then I'll go on. Now, so once we have the rules for how to compute these overlaps of this type, what PSSY did was that they introduced a non-gravitating path in this case, which is just simply given by some QDet, if you like. Again, this QDet has k degrees of freedom, just labeled by some orthonormal states I, and I'll put a subscript R on them to suggest that this is sort of the gravitational bath, which will be a stand-in for the radiation. Okay, and they considered this entangled state between the black hole and the radiation. Okay, so here's your entangled state. These are, once again, these are like the end of the world brane states of the black hole that we just described, and these are the sort of states corresponding to the non-gravitating path, and we are considering an entangled state of these two systems as a sort of stand-in or a time model for the entangled state between the black hole and its radiation. Okay. Now, in this time model, this integer k is going to play the role of time. In other words, as you vary k or as you increase k, what happens is that you're at least naively increasing the entanglement, or I should say that as you increase k, you're adding more and more terms in the superposition. So it at least naively seems that you might be increasing entanglement between the black hole and the radiation. And indeed, that's what happens, at least for small k, as we'll see in a little bit. But at any rate, so this is going to be the toy model for a black hole entangled with its radiation that PSSY considered. Okay, so just to get some practice with these kind of states, let's first compute the norm of that state, the norm of the state. So the norm is just, if it's a simple computation using the orthonormality of these basis states on the radiation, you can compute the norm and you find that it's given by a sum over I from 1 to k of these overlaps. Okay, and we just discussed that overlaps of this type in the black hole are computed by Euclidean geometries in JT gravity with end of the world branes. Now note that both the indices I here are the same. So this amplitude is non-trivial with the propagator on the brane being just 1. And so you get a k from the sum over I here. Okay, the sum over I gives you a factor of k. The n is just the normalization factor that we put in the original state. This is the same n here. And z1 is just what I'm calling the action of the gravitational, basically the gravitational contribution to the action. So e to the minus s on shell for the gravitational action. Okay, so I should have said that this, well, okay, let me say it later, but so this was just sort of a practice calculation to see how these kind of overlaps are computed. But the point here is that you set this norm to 1, and that tells you what this normalization factor is. And it's just k times z1. Okay, very good. Any questions so far? Okay, all right. So now that we have some practice with these states, we can push ahead and ask for slightly more complicated quantities. In particular, the thing that we're really interested in is the entanglement entropy between the black hole and the radiation. And so one way of computing the entanglement entropy is to use the replica trick, as you all know. In order to do that, we first calculate, so we are interested in the entanglement entropy of the radiation. So let's calculate the reduced density matrix of the radiation. This is a simple computation. You start with this state and you compute the reduced density matrix, and this is what you get. So from here, from the reduced density matrix, we can now go ahead and compute Renyi entropies. So for example, the second Renyi entropy I've written out over here. Again, it's just a matter of using the orthonormality of these i's and j's on the radiation Hilbert space. And that gives you the second Renyi entropy, like so. Now we can sort of visualize what this this second Renyi entropy looks like in the quantum mechanics system in terms of path integrals. You see, each one of these overlaps here is like a Euclidean segment. Okay, there are 2 of these overlaps, so we have 2 Euclidean segments, and they're between states I and j, and the I and j are summed over. So the fact that we have a sum over I and j is going to be denoted by these blue lines. So these blue lines just are a notation for the fact that these boundary conditions I and j are being summed over. Okay, it's just notation. But in terms of the boundary quantum mechanics path integral, you get 2 Euclidean segments like this. Now the point, as before, is that we can calculate this quantum mechanics path integral using gravity by just going ahead and finding gravitational geometries or saddles that fill in this sort of a boundary condition. Okay, and the 2 main saddle points that are of interest to us here are these 2. Okay, so note that the asymptotic boundary conditions in both these cases are the same. We have these 2 Euclidean segments in the dual quantum mechanics. The difference between these two is that the bulk geometry that we use to fill in these asymptotic boundary conditions are different. So in this case, the end of the world branes connect in a way such that the geometry is disconnected. Okay, we have two Euclidean black hole geometries, let me just say it that way. It's sort of a disconnected Euclidean black hole geometry, whereas in this case, the end of the world branes connect between the two sides, and the geometry is a connected one. Okay. Now it's a matter of simple power counting to see what the sort of factors associated with each of these geometries are. So one of the things that you should note is that because the propagators on these end of the world branes are just delta ij's, you see that there is basically one loop of these internal degrees of freedom running around on this side, which gives us a factor of k, but the normalization, you'll remember, has a factor of k in it. And in particular, the second Renyi entropy has an 1 over n squared. So the k from here cancels with the 1 over k squared, and you get a 1 over k for this geometry. Now so this was the second Renyi entropy. More generally, you can check that the factor that's associated with this geometry is essentially like k to the 1 minus n. And for the connected geometry, what happens is that you get two loops of these internal degrees of freedom. That sort of cancels out all the k dependence inside here. But one thing that I should have emphasized is that there are also these factors coming from the Euler characteristic. So remember that the Euler characteristic here is 2 because you have 2 disks, whereas here you just have one, topologically you have one disk. So you get a factor of e to the 2 times s naught here and e to the s naught here. But the normalization once again has a sort of gives an e to the minus 2s naught. So all things considered, and when the dust settles, the disconnected geometry has no dependence on s naught, whereas the connected geometry has an e to the minus s naught in it. Okay, and more generally for the nth Renyi entropy, it has e to the 1 minus n times s naught. Okay, good. So now we can sort of compare.
Hi.
Yeah.
So I have a question. So can
Yes,
we think this Renyi entropy as an expansion of 1 over k, and you are taking two contributions leading, I mean, two dominant contributions from that expansion?
Yeah. So
because
it's
you're counting.
Yes, it's you're right. We are considering two of the dominant saddle point contributions to the Renyi entropy. This is not a 1 over k expansion. This is essentially exact in k, but the sort of first of all, what we are doing is we are considering well, actually, what you're actually, no, you're right. So what is being said is that we are only considering sort of the geometries which are sort of dominant in the either the large k or the small k limit. So in the small k limit, this geometry dominates, but
Yes.
in the large k limit, this geometry dominates. Now at intermediate k, where k is roughly of the order of e to the s, you have to be more careful, and you have to account for a larger collection of not necessarily Zn symmetric saddles, which can also be done using some resolvent techniques, which were explained in this paper of PSSY. But I'm not going to need that for my purposes. So I'm just going to consider geometries which are, so this one is relevant for small k, and this one is relevant for large k.
Okay. Thanks.
Sure. Any other questions? Okay. So just comparing these two contributions, you can see that you see when k is small, then this contribution is much more dominant as compared to this one. Well, when I said k is small, I meant k is much smaller than e to the s. So when k is much smaller than e to the s, then this contribution dominates over that one. But when k is much greater than e to the s, then this contribution dominates over that one. So for small k, in other words, from here we can compute the entanglement entropy in the standard way by analytically continuing in n, and you're going to find that the answer is log k. This is essentially analogous to Hawking's answer, because remember I said this k was the analog of time, or log k more precisely is the analog of time. As k increases, you're increasing the size of the radiation subsystem that is entangled with the black hole. And so at least when k is much smaller, we find the von Neumann entropy growing as log k. But when k is much greater than e to the s naught, you get this type of saddle points dominating, and the corresponding entropy that you get from here is basically s naught from this factor here, plus you also have to account for the gravitational contribution from these bulk geometries, and that gives an additional contribution, which is analogous to A over 4 g Newton coming from the horizon of the black hole. But crucially, the point is that this entropy is k independent. So the entropy increases with k for a while, and then it saturates to something that's k independent at roughly when k is of the order of e to the s, or log k is of the order of s. And this is the sort of page curve, or the saturation of the page curve. Okay. And one last comment before moving on to gravitating baths, which is the main subject here, is that from a Lorentzian point of view, we can think of this transition between these two saddle geometries as a transition between two quantum extremal surfaces. So before the page time, this particular geometry, if you look at its Zn quotient, then it doesn't have any Zn symmetric point within space-time. And so in the Lorentzian context, this corresponds to what we might call an empty quantum extremal surface. But this saddle point has a Zn symmetric point within space-time. And when you take its Zn quotient, you find a quantum extremal surface located at the bifurcate horizon for the black hole. Okay, so from a Lorentzian point of view, it's a transition between these two quantum extremal surfaces, and this is essentially the same description that we had given before in terms of the island rule. So in other words, after page time, you find an island on the black hole side. Okay, great. So that was all I wanted to review about this PSSY model. So before I go on to considering gravitating baths, are there any other questions about this?
Onkar, I have a small confusion. So you begin with a setup where like you have two Hilbert spaces, one for the black hole and one for the radiation, right?
Yes.
And then you're considering a tensor product of these two Hilbert spaces.
Yes.
Right. So this setup is exactly like what Page considered, right? So so even before you're doing any computation, it is expected that you will reproduce the Page curve. So like in which way I should view this entire analysis?
So Page's calculation is an entirely sort of quantum mechanical analysis.
Yeah.
The non-trivial thing about this calculation, or the calculation of Pennington, Schenker, Stanford, Yang, is that this result is now obtained gravitationally, right? So when we made all these comments about this saddle dominating versus that saddle dominating and so on, these are gravitational calculations, right? Once you set up your boundary conditions in quantum mechanics, all of the other computations are done in gravity. And in particular, the entropy is also computed using gravity, right? You calculate the Renyi entropy using these gravitational saddle points. And then they also have interpretations in terms of quantum extremal surfaces in space-time. So I would say that the way to think about this is that in some sense, this reproduces the expectation from Page's argument, but from a semi-classical gravity calculation.
But here it is guaranteed that you have the gravitational system is dual to a quantum mechanical setup, right?
Yes.
So the feature is already inbuilt.
Sorry?
So this feature is already inbuilt in the setup, right?
It is inbuilt, but it's not entirely obvious how it happens from a gravity point.
So it's more like interpreting what is happening in the dual gravity, right? If that gravity has a quantum mechanical dual.
That's right. So I mean, I should be a little bit more careful. The dual here is not a purely quantum mechanical system, but it's an ensemble of quantum mechanical systems. Okay. But that's besides the point. But you're right. In some sense, that feature is guaranteed. But the paradox or the puzzle about Hawking's paradox has always been how to interpret or how to see that effect, how to see the saturation of the Page curve or the Page curve from a gravity calculation, a semi-classical gravity calculation, let's say. And I mean, this was a very non-obvious thing before.
So can I make one comment?
Okay.
Please.
I think the point of the PSSY calculation is that if they did not include the e to the minus s term that Onkar was talking about, this in the second piece, you would actually see an information paradox. Mm-hmm. So in the case of Page's curve, you never would, there is no, you don't know how you could get an information paradox if it is a purely quantum mechanical system. But because the calculation is phrased as a dual gravitational calculation, you can actually see an information paradox in the setup, and then there is a way to resolve it. And that's what makes it sort of interesting. So otherwise, in Page's calculation, you don't expect to see an information paradox at all. You're completely right. If you factorize the system, you will get a Page curve. But here the point is that you do get an information paradox because you're doing the calculation gravitationally. I just wanted to make that comment.
Yeah. So, but this expansion that you have, this diagrams, even if I don't have a gravity dual, this will happen, right? So within the Page setup itself, we can see that there is an issue, right?
Well, I mean, this
expansion has its own meaning, right? Even if you don't consider the gravitational.
But I think right? So the particular replica wormhole saddle that they're filling in is a gravitational prescription.
Okay. Mm-hmm.
Otherwise, you don't have that. It's a prescription in the gravitational language.
That's
right. But I should let Onkar speak. I mean,
or otherwise, yeah. So I understand that point. So I'm just trying to see, like, even if I don't have the gravitational dual, like, will this expansion has a meaning in the quantum mechanical setup itself? Or is it something which is there only because you have a gravitational interpretation? Like,
presumably there is, I mean, even in other other matrix models which are other than the ones dual to JT gravity, there are similar diagrams you could draw, and you could sort of make up Hawking's information paradoxes in sort of a matrix model language. I presumably that's correct.
Yeah, so my question is more like, so let's say I forget about gravity. If I have a quantum mechanical system, so by just restricting to few initial terms, can I see information paradox always? So even in a quantum mechanical system, and just interpret that. See, I'm seeing this paradox because I am not considering the complete contribution to this computation.
Presumably that's correct, but it's only. Okay, that's presumably that is correct. You can, but it's interesting here because it maps on to the dual Hawking's paradox in gravity, right?
Yeah.
Otherwise, sure, you could consider a paradox like that, but my opinion is that it becomes. Yeah, go on.
I think you'd have to see the calculation semi-classically in the purely quantum mechanical system, and I think that's non-trivial.
Okay, good.
That's fair. Yeah. Any other questions or comments?
So I have a question. So I couldn't quite understand this picture. So the quantum extremal surface, what do you mean by empty quantum extremal surface? I mean, if we want to consider the entanglement OH, with the
Yes.
surfaces. So how do we
Yes, yes. So
see this from the picture?
right. So the entanglement wedge of the CFT dual to the black hole is the entire black hole spacetime. Okay. And the entanglement wedge of the radiation is everything semi-classical in the bath. That is what one means by an empty quantum extremal surface. From the replica trick point of view, it's a surface which is not within, like like the ZN symmetric point in this geometry is not inside any of these space-time regions. And the other quantum extremal surface is presumably more clear because the entanglement wedge, okay, so in the other one, the entanglement wedge of the dual CFT is just this region out here that I'm pointing to right now.
Okay, this triangle.
And
okay,
right, and the entanglement wedge of the bath will be all the semi-classical stuff in the bath plus this blue region in the spacetime.
okay,
Is that clear?
okay. So entanglement surface is just a point. Sorry, QS is just a point. Okay.
That's correct. In this case, it's a point because we are in two bulk dimensions.
Oh, okay.
Yeah.
Okay, thanks.
Sure. Any other questions? Okay, so if not, then I'll move on to the main topic, which is the question of what happens if we consider gravitating baths instead of considering non-gravitational baths, which was the setup in the PSSY paper. Now, the simplest time model for this, for considering gravitational baths, as Chetan was mentioning a while back, is a setup where we have two black holes and we entangle them together. Okay, so just imagine a very similar picture to the one that we just discussed, except replace this non-gravitating path with a different black hole. Okay. Now, just from this discussion over here, one would naively expect that the following sort of picture is true. Well, before page time, there is an empty quantum extremal surface, just like here. But after page time, you could have one of two quantum extremal surfaces, which either is the bifurcate horizon of the left black hole or the bifurcate horizon of the right black hole. And the smaller of them perhaps dominates. So at least a naive expectation would have been that if we entangle two black holes, then after page time, one of these two surfaces dominates, and then you get an island in either one of these spacetimes. Okay. Now, what I want to explain in the next few minutes is that this naive expectation is not always correct. In fact, we are going to see in this model, in this PSSY model with two black holes entangled with each other, that what happens is that you get a sort of entanglement-induced Hawking-Page transition, and you, instead of this disconnected black hole geometry, one gets a connected black hole geometry, where these two black holes are sort of connected together by a spatial wormhole, or an ER equals EPR wormhole. Okay, and so in this case, the conclusion is going to be that this correct geometry after the page time does not have any islands, but instead it has a wormhole, a bridge, if you like, connecting between the two sides. And also note that in the Lorentzian geometry, there are no end of the world branes anywhere. Okay, so we'll see how that happens. Okay, so to see that, let's consider, as I said, an entangled state of two black holes. Okay, so remember that before we were considering a state of the black hole entangled with some radiation, non-gravitational radiation. But here we want to consider a black hole, say black hole left, entangled with another black hole, just black hole right. Good. So just to get some practice again, let's try and calculate the overlap of this state with itself. Very simple to calculate the overlap, and you get this expression. You have these two factors of psi i's overlap psi j. Okay. So the Euclidean, just like before, the Euclidean path integral in the dual quantum mechanics which computes this norm or this expression here, is very similar to the second Renyi entropy that we encountered in the previous discussion. It basically has these two Euclidean segments. And remember from before, this notation with the blue lines means that there is a sum over I and j. So it's this sum here. Okay. And so this is the boundary quantum mechanics spectra. And just like before, the way we are going to go ahead and evaluate this boundary quantum mechanics expression of the Euclidean path integral is that we are going to fill it in with gravitational geometries, bulk geometry. Okay. And just like before in the previous discussion, we have there are two types of geometries that you can fill in. There's a disconnected saddle and a connected saddle. I should emphasize that here we are not talking about a Renyi entropy or anything fancy. This is just the norm of this entangled state of two black holes. Okay, so it's just the pure vanilla bulk geometry dual to the state, if you like. Okay, but it's the same. The mechanism is the same. There are these two saddle points which could dominate at either small k or large k. The connected one has one loop of these internal degrees of freedom, so it comes with a factor of k. It has an Euler characteristic of 2, so it comes with e to the 2 times s naught, and z1 squared is just the rest, the contribution from the on-shell action of the gravitational path integral. Whereas in the connected saddle, we have these two loops of the internal degrees of freedom, so that gives k squared. The Euler characteristic is 1, so we get e to the s naught. And finally, z2 is everything else. Okay, the contribution from the on-shell action. And once again, we see now that when k is small, okay, then this geometry is going to dominate, because note that this has an e to the 2 times s, whereas this has an e to the s. So when k is much smaller than e to the s, this geometry dominates. But when k becomes large, much larger than e to the s, then because this has a k squared and this has a k, you're going to find that the connected saddle point dominates. Okay, and so this transition between these two saddle points, before we interpreted it as a transition from a transition in the sort of replica trick calculation, but here with two gravitating, with two entangled black holes, this transition becomes a transition at the level of just the norm of the state. Okay, now we could try and ask what is the interpretation of this connected saddle. So the way to do that is we simply cut the surface at the time reflection symmetric slice, and similarly here. So if we, for example, think about the disconnected saddle first. If we cut the disconnected saddle at the time reflection symmetric slice and evolve it in Lorentzian signature from going from there, what you find is a geometry like this. Okay, so the time reflection symmetric slice is roughly the t equals 0 slice here, this slice here, and note that it has these two end of the world branes, because these branes are also on the time reflection symmetric slice in this saddle point. But if you take this saddle point and you cut it at the time reflection symmetric point and then evolve it in Lorentzian signature, then you get an eternal black hole, which has no end of the world branes, because, well, the time reflection symmetric slice here knows nothing about these end of the world branes. Okay, and it's just the ordinary ER equals EPR wormhole connecting the two sides, or the eternal black hole, if you like. And so when note, as I said, this connected saddle point dominates when k is much greater than e to the s. And so that's the region in which this sort of naive picture of two disconnected black holes is not correct, but the correct picture in this case is this this connected saddle point, with the these two asymptotic regions connected with a wormhole, with a geometric wormhole between the two sides. Okay.
So Onkar, one quick
yes.
question.
Please.
So in this, if you said that, so what happens if you change the number of flavors in your end of the world brane? I mean, how does the wormhole picture change? I mean, I'm a little bit confused about why that doesn't play any role at all in your second picture.
You mean this K?
Yeah, I'm kind of saying it kind of intuitively, in the sense that, like, the fact that this eternal black hole picture that you evolved from this equal time, it's not equal time, what is the time symmetric slice?
Time reflection. Yeah.
That seems to know nothing about the number of flavors of the brane, right? So that seems a little, how should one think about it? I'm a little confused. Maybe you can say a couple of words about it, and maybe that will make a little bit more sense.
So sure. So these internal degrees of freedom K are in some sense, it's what this is saying is that somehow you can imagine cranking up these internal degrees of freedom to as large as you want, but when they exceed when they exceed e to the s naught, the extremal entropy, then sort of gravity comes in and cuts that growth off, and this transition is sort of a manifestation of that. The fact that you can't just, so in other words, what is happening roughly is that these states which are labeled by K or these internal degrees of freedom I are becoming non-orthogonal after that point. They're sort of becoming linearly dependent. That's roughly why this cutoff happens, or why gravity cuts off this growth. Does that help?
Yeah.
Okay.
That does clarify.
Okay. Any other questions? Okay, so this was the discussion of the norm of the state. So already at the level of just the norm of this of the state of these entangled black holes, you can see that there's something interesting happening, and including a gravitating black hole region that's entangled with your original black hole gives rise to some interesting new physics, in particular this wormhole as opposed to islands. Now, I note that it's already 1 hour, so I just wanted to confirm whether I can go on for a few more minutes.
Yes, please, Onkar. Yeah, you can take.
Okay.
We are not very strict.
Okay. So I should be done in 15 minutes or so, if that's okay. Okay, so that was just the discussion of the norm of the state. But now we could also go ahead and ask a more refined question like that, like what happens to the entanglement entropy in this context with two black holes which are entangled with each other. So once again, that can be done by computing Renyi entropies. And I won't go through all of the details. They're very similar. You just start with the state, you compute the reduced density matrix on, say, one of the black holes, and then you compute trace rho to the n. So here I've just shown for you the case of the second Renyi entropy. Now, in the second Renyi entropy, what you find is that there are 4 of these Euclidean segments. That happens because there are 2 black holes which are entangled with each other. So once again, the way to compute this in gravity is to go and find all possible gravitational saddles that can fill in these 4 Euclidean segments at the boundary. For the present context, these 2 saddles, once again, as before, these 2 are the relevant saddles. There's a fully disconnected saddle where all of the branes just connect up each of these Euclidean segments. And then there's a fully connected saddle where the branes connect together all of these segments and the geometry is fully connected. Okay. There are in fact 2 more ZN symmetric saddles, which I haven't drawn here, but I'll mention them a little bit later. Now, if you work out what the contributions of the disconnected and the fully connected saddle are. It's not very hard to do that. You can just convince yourself that these are the expressions. And a little bit of inspection will show you that once again, when k is much smaller than e to the s naught, this disconnected saddle dominates the Renyi entropy. And when you calculate the von Neumann entropy from there, you get a log of k. So this is again the same kind of Hawking growth of the entanglement entropy. But when k is much greater than e to the s naught, this fully connected saddle point dominates. And when you calculate the von Neumann entropy from that Renyi entropy, you get exactly s naught plus the contribution from the the value of the dilaton at the bifurcated horizon corresponding to so it's not hard to check that it's actually the bifurcated horizon corresponding to this this eternal black hole. Okay, so in other words, when you go through the calculation of the replica trick, the Renyi entropy, what you find is that at k much greater than e to the s naught, the von Neumann entropy is indeed computed by this bifurcated horizon in the eternal black hole or in the connected geometry. Okay, so the late time quantum extremal surface is indeed in this connected saddle point, the dominant saddle point, the saddle point which is dominant at after the page time. Wonderful. So one last thing about this is that, as I said, there are also a couple of other saddle points which are ZN symmetric that were not included in this case, and it's just very easy to confirm that they don't contribute, because either when k is much smaller than e to the s naught, or when k is much larger than e to the s naught, then these two saddle points are not relevant. It's these two which either of these two which dominates the calculation. But I just wanted to mention that this was the reason why we didn't consider these other two saddle points. So the moral of this part of the discussion is that including gravitating baths, as we've discussed, can lead to some new physics, at least in some models, which is to say that instead of finding islands, you can end up finding these sort of wormholes connecting the two regions after the page time. Okay, so I wanted to also tell you a little bit, maybe very quickly in 5 minutes, what happens if you consider other types of entanglement or other types of coupling between two gravitating regions or two black holes. So for example, one thing that you could ask is what happens if we take two black holes which are not entangled with each other, couple them together with some interaction at some time t equals 0, let's say, and then evolve them for a long time in real time, and calculate the entanglement entropy after the time evolution. So in other words, is there a Hawking page transition like the one that we found in the case where you actually have real-time coupling between the two black holes? And so again, we considered models like models of this in JT gravity. There's a little bit more detail in these models, because in order to mimic this coupling between the two black holes, what we had to do was we considered some bulk matter. In addition to the JT gravity, we considered some bulk matter in the bulk geometries, which is taken to be just a 2D CFT in this case. And the coupling between the two black holes is turned on by turning on a coupling between the two CFTs. So in other words, this is pretty standard of many of the calculations that have been done recently. So I'm sure many of you are familiar with this, but the way this coupling works is that you turn on transparent boundary conditions between the bulk CFTs at the asymptotic boundary in the Lorentzian section. Okay, and so from a dual quantum mechanics perspective, this is essentially equivalent to taking two black holes in a product state, turning on some interaction between them, and then evolving for a long time t. Okay, with this unitary. So as a function of time, because this Hamiltonian turns on some interactions between these two systems, we expect this to generate entanglement between the two black holes. But in this case, we don't, in a kind of a trivial way, we don't find any Hawking-Page transitions. It's kind of trivial to see why, at least at the level of the norm. So if you compute the norm of the state, then what happens is that then there's an e to the minus ith from the ket, but there's an e to the ith from the bra, and inside the norm, this obviously cancels out. Okay, so the norm of the state is actually just time independent, and so if you start with a product state, the norm of that state is just time independent, and so there is no, you don't expect to find any Hawking-Page transitions in the norm of the state as a function of time. But you could still wonder whether if in the computation of the entanglement entropy, there's a phase transition in the quantum extremal surface to some connected saddle point in the replica, some sort of a replica wormhole. So we did that calculation as well in the paper, and you can find all of the details in the paper. I'm going to skip over the details. The punchline though is that what happens in this case is that the Renyi calculation, or the Renyi entropy, is dominated by these type of saddle points. So remember in the previous discussion, we had ignored these saddle points because they don't matter in that case at very small or very large k. It turns out that in the real-time coupled black holes, the analog of these saddle points is what dominates at late times. These sort of segments jutting out here are the Lorentzian sections, so you can ignore them if you don't want to follow all the details. But the point is that it's these two saddle points which dominate, and the Lorentzian picture dual corresponding to these saddle points is precisely the picture where either one of these quantum extremal surfaces in the disconnected black hole geometry takes over after Page time. Okay, and the connected eternal black hole geometry is subleading. Its contribution to the entanglement entropy is suppressed by e to the minus s in this calculation. So in this calculation, where we turn on a real-time coupling between the two black holes, one indeed finds this naive expectation of one of these two quantum extremal surfaces is dominating and forming an island as opposed to a bridge is realized. But in the other model, where we considered the entanglement between internal degrees of freedom on the end of the world brane between the two black holes, you find bridges as opposed to islands. Okay, so let me, I've gone on way over time, so let me just conclude. We found that including gravitational baths can have important physical effects. For example, in one of the models that I showed you, it leads to a Hawking-Page transition, which sort of avoids an island, but instead forms a wormhole, realizing the ER equals EPR paradigm. And this effect is not universal, as we just discussed. So this wormhole formation is not realized, at least in any obvious way, in a scenario where we couple the black holes together in real time and evolve them. In that case, we find islands. And for future questions, one of the questions that comes to mind is, well, what is the general condition for formation of either a wormhole versus islands? So when do we form wormholes versus when do we form islands? Is there some general criterion that we can use to identify these two cases. And another question that comes to mind is whether we could indeed form a wormhole using some real-time evolution. In our paper, you can find all of the details. We tried several ways of trying to realize this this possibility, but we don't have a very clear answer as of now. And there are other questions like, can we also realize these ER equals EPR type bridges in higher dimensions and so on? So I'll stop at that point. And thank you for your attention.
Thanks a lot, Onkar, for such a nice talk. We still have time for questions, please.
Hi, Anita, can I ask?
Please. Yeah.
Hi, Onkar. So there was this paper by Maroff Maxfield, right, where they also looked at the, asymptotically flat case where you don't have a non-gravitating bath anyway. Okay. And there the picture they had was that, before page time you have these standard wormholes, this Perry-Strominger wormholes, and after page time you get these wormholes which connect different copies of the replica space-times, right? And then in that contribution dominates. They were computing the swap entropy, and they said that the contribution of the other wormholes dominate over the more classical wormholes when you're after page time. So I was wondering if there is is there a connection between your picture here and the one that they had there?
Yeah, that's a good question. Not that I can obviously say, because in the case where we have some real-time coupling between, as I said, in the case where we have a real-time coupling, the replica wormholes which dominate are this ones, which correspond to these more sort of conventional quantum extremal surfaces, or the island quantum extremal surfaces. For the wormhole saddle to dominate, or the eternal black hole to dominate, we kind of really need these internal degrees of freedom, and we need to build the entanglement between the two black holes using those. So perhaps if one considers the Maroff-Maxfield Lorentzian setup with end of the world branes and includes sort of internal degrees of freedom like these in their setup, maybe one could try and realize this in their case. But okay, but I'm not entirely sure. So I should probably not guess off the top of my head. Yeah.
Thank you.
Yeah.
Any other questions?
Hi, I have a question.
Yes.
So the geometry that you have neglected, the partially connected geometries, so they are crucial to understand what happens at the page time, right? Because there are because you are considering two limits where this k is small and k is large. But what happens at the page time? Suppose some other quantities like complexity, when they show some jump due to the change of these extremal surfaces. So to understand these quantities, you need to understand these what happens at the page time, right? This connected this kind of geometries.
You're right. So if you want to understand the detailed nature of the page curve,
Right.
like the precise nature of how it turns over and saturates, then to get all of those details on the nose, then you have to include all of these. Not only these, but you also have to include other other possible saddle points which are not ZN symmetric. So here I was just drawing the ZN symmetric ones, but in general there are also non-ZN symmetric saddle points which you need to include. Those can be included, by the way. They can be included using resolvent techniques, but they're not relevant. They're not super relevant for the broad strokes physics. So I didn't describe them in any detail. But you're right. If you want to get all the details of this page curve, in all of its glory, then you need to include those other saddle points. But I mean, I don't know whether you said complexity, but I mean I don't know whether complexity, my expectation is that the complexity doesn't show any funny features at the page time, because the complexity is expected to grow till
No, this is kind of the subregion complexity. I mean, the compute the volume between the extremal entanglement wedge of this radiation subregion and this and the quantum extremal surface. So this, as soon as the surface changes to another surface, so the volume change. So at the page time, you would expect that there is some kind of discontinuity of this quantity, right?
I see. Interesting. Okay. Fair enough. That sounds interesting, because usually we don't expect the complexity to show funny behaviors until exponential times. But what you're saying is also interesting.
I mean, that happens only at the page time. So you have to fully focus what happens at the page time, not before the early or late times. But this discontinuity happens right at the page time. So this you need to consider, I guess.
That sounds interesting. Okay.
So Onkar, I had another question actually. So in the beginning, when you look at the end of the world brane configuration, and it was dual to the the boundary state.
Yes.
Like the I, with the double notation. So this I, as you said, this I was in the dual theory, which was the ensemble average, right? It was a state in the theory because the couplings were random.
You can think of it as a random state.
Like this, yeah. So if your boundary theory was just not in a higher dimensional case where it was just a unitary CFT, and if you start with a state like I mean, if the end of the world brane picture, I mean, how much will it change if the...
Yeah, that's a wonderful question. I don't know the answer to that question. Because in part, the ensemble average interpretation of higher dimensional gravity is not well understood. I suspect that at least in some toy models, you can construct, well, you can of course construct such random states in higher dimensional CFTs as well. And I suspect that at least in some simple enough toy models, one can argue that the bulk dual of such random states are end of the world branes in, for example, ADS3. But to my knowledge, this hasn't been fleshed out in complete detail. So I don't know the answer to that question. Whether
some of this end of the world brane is like important to this. So in the sense that this ensemble average is very crucial to the story right now.
That's correct. Indeed, you're right.
I think the end of the world branes are an explicit way of providing microstates, right, in these systems.
But if the boundary theory is unitary, even there will be microstates. But my question was whether they will be end of the world brane configurations of that type Onkar described.
Yeah. So So I think the question of providing explicit end of the world brane interpretation for the black hole microstates in higher dimensions would probably be difficult. Yeah.
That's right.
I mean, difficult, or
but
at least you would need something like what Onkar.
Yeah. But one expects, following the logic of PSSY, one expects, or at least I expect, that the physics of end of the world brane states in higher dimensions as well is related to some sort of random states like this.
Okay.
Right. That's right. Yeah. But the question is whether it is a phenomenological way of describing these microstates, or whether they are phenomenological in the sense, like as a way of capturing their the fact that there are many of them in some sense, and like they can be sort of sorry, go ahead.
Yeah, no. If you take a state in any good for super young mills, then like a state I, then do we expect the dual to have in what limit do we expect it to have a end of the world brane type dual interpretation, right? I guess that was
So I think that I mean naively, I kind of think of their construction, this PSSY way of putting this end of the world brane as an explicit way of microstate data for a black hole. That's how I think about it. But so on the other hand, in higher dimensions, we have explicit microstates. So it's not super clear. But your question is obviously a great question. But
I mean, like even if you take fuzzball geometries, they are not end of the world brane type geometry.
Yeah, exactly.
So my impression, and this is obviously not a precise impression, but a very vague one, is that if you consider energy eigenstates, so many of these fuzzball geometries are more like energy eigenstates. So perhaps the more general picture is that things like energy eigenstates may not have natural, like they may be
right. Okay. Yeah, that makes sense.
But if you consider sufficiently averaged sufficiently average superpositions or random superpositions of fuzzball states or energy eigenstates, then one may land on a reasonably geometric state, which is described by an end of the world.
Okay. So that's consistent at least with the hypothesis.
That is my impression, but this hasn't been shown, as I said.
I think it is. It might also be that so to the extent that a true set of microstates can be replaced by an ensemble, I think this averaging that you're talking about might also be useful.
Correct. I agree. That's the other thing, which is that the ensemble averaging interpretation of holographic CF or supergravity in higher dimensions isn't completely understood. So. But I think this is a great question, because the ADS BCFT prescription that is often used in higher dimensions can perhaps be put on a much more concrete foundation if something like this can be realized in higher dimensions.
So you're saying in 3D, maybe there is something like this could be done, at least in 3D.
Correct. In 3D, there is some hope. Yes.
Okay, so if there are no other questions, I guess, Onkar, it must be very late for you. What is the time there?
It's not that late. It's 11:25. Yeah.
Excellent. So, any other questions? I wanted to ask you a question right in the very beginning. I should have asked.
Yes.
So you had this picture where you had this wormhole that was connecting up two different regions, and in the very first slide, elongated wormhole. So. So is the correct physics interpretation that as the black hole evaporates, the wormhole also changes and probably grows, and then somehow it contributes more to the saddle point? So it's a dynamical thing that must be going on, right?
Well, so in the toy model where this wormhole forms, in our case, it's the one where we have these internal degrees of freedom on the end of the world brane, right? And then we just sort of by hand entangle them together by considering superpositions of these two black hole states. So it's a little bit hard to sort of give it a dynamical interpretation, because we are including these superpositions, or this parameter k that I mentioned. That parameter k is somehow just put in by hand, and then you crank it up. And when k becomes large enough, there is a Hawking-Page transition. So in some sense, it's analogous to the Hawking-Page transition that we are usually familiar with, where we, you tune some parameter, right? We tune like the temperature of the dual CFT thermal ensemble. Then there's a Hawking-Page transition. So here we tune the, if you like, the the rank of the superposition, like how many states are included in the superposition. That is tuned, and when that becomes large enough, there is a Hawking-Page transition. But as I said, it's a bit hard to give it a real-time dynamical interpretation.
But in a realistic scenario, what do you think is going to happen? Or what is the picture that one should have in mind?
Right. So in the realistic scenario where we couple the two black holes in real time and evolved it in real time, right? That is presumably the realistic scenario. And there we couldn't find this wormhole formation in any obvious way. So as I described, in that case, there are a different set of saddle points which dominate, and they form islands as opposed to forming wormholes. Or at least my impression is that in these realistic settings, one doesn't form these classical wormholes. So when I said wormhole, I meant like a classical wormhole. Right. So in these realistic real-time pictures, you don't end up forming classical wormholes, but you form islands, and maybe these islands have interpretations in terms of some more exotic quantum wormholes. I'm not sure. Yeah, but I mean, that is not to say that one cannot realize a classical wormhole in real-time evolution. It's just that we tried several different models and we failed at finding classical wormholes. But it's not like we've proven a no-go theorem or anything like that. So it may be that if you're sufficiently clever, then you can build classical wormholes with real-time evolution. But we failed at doing that.
Okay.
So I can make one comment about doubly holographic settings, where if you have so the picture is sort of symmetric between the bath brane and the the black hole brane. So, and that sounds, I mean, I don't, I haven't looked at your this time evolving thing that you mentioned. So, I mean, I should look at your paper, but it sounds vaguely similar to what you're saying, in the sense that there is some sort of a there's some sort of a symmetry between in our picture, at least in the doubly holographic thing, we find some sort of a symmetry between the gravitating brane, what is called the gravitating brane, and what is called the bath brane, because both have black holes. And there is I don't see a particular difference between the island being on either side. So that vaguely is reminiscent of a symmetric wormhole type setup. But on the other hand, it's a doubly holographic setting, and the interpretation may be a little bit
right. So in that setting, I would say the wormhole is a higher dimensional. It's like this doubly holographic.
Exactly.
Wormhole.
I agree. Yeah.
It's not. So we were after wormholes, which are singly holographic, so to say. But I see what you're saying, Chetan. Yeah.
Okay, so maybe one final question I can ask you, Chetan, and you, is that how much of this story do you expect is going to hold for flat space black holes and the black holes at the center of our galaxy?
That's a great question. Chetan is the expert on this, so he should really.
It's not that I'm an expert; I'm opinionated. There's a difference.
Yes.
Go ahead.
Yes, that's great. Yeah.
Go ahead.
No, I mean, it's a complicated question, but I think that flat space, so I think essentially the reason why two kinds of holography exist if you have holography in flat space as well, and if you take the near horizon limit, you again have holography in terms of ADS-CHEP-th. And I think of this coupling to this asymptotic region is basically a form of coupling to a bath. That's the way I look at it. And everything that I'm doing, it kind of makes sense to me in that picture. So, but I think that, so there is clearly more work is needed. And I don't want to be too, I said I'm opinionated, but I'm willing to change my opinions as well. So
yeah, great.
My understanding is that many people, including Chetan and Alok and others, have done calculations using the island formula in asymptotically flat geometries. And at least the island formula is well defined. So you can apply it to other asymptotics as well. Now, whether you can find these wormholes, the kind that we were describing today's talk, is not clear, because we really relied very heavily on ADS-CHEP-th. But the island formula, as far as I understand, can be applied away from ADS asymptotics.
That's it.
And I think you mentioned in the real-time setup, you actually do find islands. That's what you mentioned, right?
Yes, that's right.
Okay.
Excellent. That was great. Anyway, so I guess there are no further questions, but it was very nice having you over virtually, Onkar.
Thank you so much, and thank you for inviting me. It was a lot of fun.
Yeah, exactly.
Great.
Yeah, good to see you after a while.
I will stop recording and then